All right, I wanted to spend some time just within Unit D here. There are some chemistry calculations that come back up, and I hope that some of the information you remember from Unit A, which was the chemistry unit in regards to moles and so on. Also, the issue of algebra comes up again because you have to manipulate some formulas to isolate certain variables. So what we're talking about here is specific heat capacity, and the formula is Q equals mc delta T. Q is the amount of heat in joules. M is the mass of the substance in grams, and change T is the change in temperature in degrees Celsius. Now, these values right here that we have are very important. These are the specific heat capacity values for various substances. Now, these values will always be given to you, but we have to refer to them when we calculate some of these. So essentially what these questions are going to do is they're going to ask us to solve for one of these variables. And what we have to be able to do is take the information and input and then isolate the variable that we want. So I'm going to show you a few here, and hopefully that'll be enough to kind of give you a kick in the right direction. So I'm going to go down here. There's an example, which of course you can read on your own. If I go over to page 2, it says, how much energy is released when 35 grams of water cools from 25 degrees to 10 degrees? So what we're going to do is we're going to go Q equals mc delta T. Q equals, now if you remember, we want to have, I go back, mass has got to be in grams, so that's perfect. So we'll go back here and we have 35 grams. Now, the C value is your specific heat capacity of water. Now, this is liquid water, so we're going to go back, and that should be, we'll count that as this state right here, 4.19. So 4.19 joules per, I believe it's gram degrees Celsius. Yes, gram times degrees Celsius. Now we're on to the temperature. Now, you see, you have to be very careful here, everyone, because remember, change in T is calculated by going temperature final minus temperature initial. So in this case, what we have is our temperature final was 10 degrees Celsius minus our temperature initial, which was 25 degrees Celsius. Now, yes, in this case, what you actually are going to get is a negative number of negative 15 degrees Celsius. Now, why is that? If you think of this, it says how much energy is released. That means we are giving away energy. So if you think of it yourself, you've given away energy. So now are you in a positive energy state or a negative energy state? You have given energy away. You have you have become minus. You have given away energy. Now what you have to do is you simply just multiply these values. So give me a moment and I'll do that here for you. So we are going to get 35 times 4.19 times negative 15. So it gives us a value of negative 2199.75 joules. One issue we have here is significant digits. And if you look, we need to have, in our question, we need to have 2 significant digits, okay? And this is actually going, and in order to do this properly, we're going to have to go into scientific notation. So we need to have 2 significant digits, and this is going to round up. So what we're going to have is 2.2 times 10, 1, 2, 3 joules, and sorry, that's negative. That's your Q value. That's how much energy is released when we cool water from 25 degrees to 10 degrees. We are releasing energy. We're giving it away. Oh, pardon me, wrong button. If you look at question B here, this is going to be essentially the same question. I'm not going to calculate this one to the full degree, except just want to point out a couple of changes here. First of all, the mass. You see, the mass is in kilograms. So what you would have to do is take 1,000 kilograms and change that into grams. Okay, I'll leave that up to you, but that's essentially how this works. Another issue you have is the C value. This time we are working with seawater. So you would have to go back and find the specific heat capacity for seawater, which is 3.89. Okay? Once you have that, you're going to have to, look at sig, dig, significant digits. Also, in this case, I just want to point out that the change in temperature, we have gone positive. So we have gained, in order to heat up, you must gain energy. Therefore, our answer at the very end, whatever it is, it must be positive in this case. Okay? Now, here, what I want to show you is how the calculations change. Now, you will have an answer key for all of these, and I don't want to go over every question because I do want to let you have a chance to figure these out. But I am going to show you here, what you have is so Q equals MC delta T. And what you need to do is, this time, figure out a different variable. So, we have, first of all, you have the issue of 100 kilojoules. Well, everyone, we need this to be in joules, because if you go back to the first page, if you look, our Q must be in joules. Therefore, we have to change kilojoules into joules. So what you're going to do is take 100 and you're going to multiply that by 1,000. Okay, and that's going to give you 100,000. So we're at 100,000 joules. So that's my Q value. I'm going to put that in. So 100,000 joules. You're solving for your M value. Your specific heat capacity, we're dealing with water, so that's 4.19 joules, grams, degrees Celsius. And our temperature change, it says here that we raised our temperature by 35 degrees. So that will be 35 degrees there, and it's positive because we're taking in energy. My opinion would be, in order to isolate this, the first thing I would do is I would multiply these two values on the right-hand side. 4.19 times 35 gives you 146.65. Then we'll undo the algebra by going the opposite. That's multiply, so we'll divide. We'll do the same thing over here. I'm going to have to put the answer over here, everybody. Sorry about that. So 100,000 divided by 146.65 gives you 681.89 ... and that should be in grams. But we have to go to 3 significant digits, so that will be 682 grams is your final answer. What I'm trying to point out here is, I don't think the math is especially hard, but you have to watch for a few things. You have to, first of all, watch for conversion of units. Then you have to ensure that you can do the algebra that allows you to properly isolate the variable you're looking for, like we did in this question. Okay, if you look at D, it's essentially the same question. It's asking for the mass of air. Again, just a few different changes there. Okay, I'll do E for you. E is a little bit different because this time they're asking for a specific heat capacity. So Q equals MC delta T. Our Q value is 2334 joules. We have a mass of 40 grams. The units are proper. We need C. Our change in temperature. Okay, change of temperature, 15 degrees. So we assume that's positive. We must be going up 15 degrees Celsius. So what I would do is I would multiply these two numbers. Remember, multiplication, the order doesn't matter, so we're going to multiply 40 times 15, and that's going to give me 600 right on the nose. I need to get C by itself, so divide by 600, divide by 600. I'll put the answer over here. So 2334 divided by 600 gives me 3.89. And that's going to be, now remember, the units for a specific heat capacity are joules, grams, degrees Celsius. We do have to change that into 2 significant digits, so it would be 3.9 joules, grams, degrees Celsius. That would be your specific heat capacity of that substance. And you can look here now, F is going to be essentially the same question. Just all they're doing here now is they're going to be asking you to change. You're going to have to change that into joules. Okay. We're going to move on. I hope, if you go back here, I hope that that's a good enough review of that. It's not very hard. It's not very difficult. It's just you have to make sure that you can calculate for the variable you're looking for. And that's essentially the straightforward calculations for specific heat capacity. The next part that I wanted to go over with you was the heat of fusion and vaporization. Now, basically what we're looking at, it's right here. These are the definitions. The amount of energy required to melt 1 mole of a substance is called the heat of fusion. On the other hand, the amount of energy required to convert 1 mole of a substance from a liquid to a gas. This has to do with phase change. And you're going to come across this very much more in Chemistry 30 if that is a course that you take, because you'll get in, well, I'll just leave it there. Come back to Chem 30, you'll do a lot of work with graphs and calculations. Your formulas here are, I would say, even easier than the Q equals MC delta T. You just have to know which one you're using. Here's what your units stand for. Q is the amount of energy. This time it's in kilojoules. N is number of moles, H, heat of fusion, vaporization, so on and so forth. So what you have to know is these are some values for you. So you have heat of fusion, heat of vaporization. So please remember, okay, if we go back, heat of fusion is the amount of energy required to melt 1 mole of a substance. You have to melt it. So essentially you're taking it from ice, and if we're dealing with water, the heat of fusion is you have to melt it. So you're taking ice and changing it into water. So these are your given values. They will always be given to you. You do not have to memorize any of these values, okay? The one thing that comes up here, everybody, is if you look at those formulas, okay, if I go back 1 page, look at that. That N creeps in there. And that is the number of moles. Well, you know what they're going to start doing? If you remember back to Unit A, that's going to be remember the molar mass calculation, number of moles? So although this is easy, sometimes they're going to make you calculate and mess around with that N value. It's also going to test if you can write formulas. So here, we'll try a couple. So again, remember, I'm just going to show you this here. Remember the formula was mass equals moles times molar mass. Okay, that was one of your units that you might, I hope that you recall that. Please also remember that you have to know how to calculate molar mass. So in this case, we're dealing with water. So remember, you have two atoms of hydrogen. So remember, hydrogen has an atomic molar mass of 1.01 grams per mole. How many of them do we have? We have 2. So that's 2.02. Then we have an oxygen. The atomic molar mass of oxygen is 16. We only have one of those. So in total, our molar mass of water is 18.02 grams per mole. Okay. So you have to really be careful here. So what they've given you in the question is we have a mass. Now we have a molar mass. We need to figure out our moles. Please recall that this formula rearranges into N equals mass divided by molar mass. Plug in, so you have 45 grams divided by 18.02 grams per mole. And you can see the answer there is 2.5. So I'm just telling everybody that although these calculations are, maybe not the most difficult, you've got to remember back to Unit A in regards to how to figure out molar mass, how to use this formula to isolate moles. That comes into play here again. Okay, so we will just try a couple examples here. So it says, how much thermal energy is required to melt 4.25 moles of ice at 0 degrees, a liquid, water, so on and so forth. So first of all, I'm going to go back. I'm going to look. Remember, we're dealing with melting, so that's going to be heat of fusion. So I'm going to go Q I'm going to use this formula right here. Q equals NH fusion. Okay. This is a very straightforward question, and it's really nice because, well, we almost have everything we need. We have the number of moles. It is 4.525 moles. All right. Now, what is our fusion value for when we melt water? So we're going to go back to our table. Okay. It's right there. 6.01 kilojoules per mole. Per mole. That simply is going to be a multiplication question. And so I'm just going to plug this in here. That's going to give you 27.195 ... kilojoules. Please remember, when we're dealing with heat of fusion, heat of vaporization, your Q value is in kilojoules. Please remember that. Significant digits, well, it's kind of an ugly example. They wouldn't go to 1, but so on. Let's say they even wanted to go to 3. That would be 27.2 kilojoules. That's kind of a weird example because of the 1 and 1. They're not going to do that to you. Same thing here. Number 2 is very much the same, except this is maybe now, the only difference here, you're going to use Q equals NH of vaporization, use a different value. See, they've given you your moles. You would figure out this value for water and go from there. Now, you know, I'm not really seeing too much of a change here. So this, what we're doing here, how much energy is released when 4.23 moles nitrogen gas condenses into liquid nitrogen without any change in temperature? Well, same thing, Q equals. Now what are we doing? Is this going to be fusion or vaporization? So it says here, condenses into a liquid, okay? So you're gonna have to go from there. So if you really look at this, what we have is we are going from nitrogen gas, and it says we are condensing into nitrogen liquid. So is that fusion or vaporization? Well, it's going to be H vaporization, and go from there. Find your value from the table. So hopefully, if back in this table, there should be one here for nitrogen. Oops, sorry. There it is. That's the one you would use in that question. Okay, you can see how this goes on and on and on and on. Let's see here. Oops, sorry, I should get rid of that line. How much heat is lost when 63 point... Okay, so 5 is a little bit of a different question. So we are going to be, it's steam condensing and forms a liquid. So that's going to be Q, pardon me, Q equals NH vaporization. The problem here is we don't have our moles. We do have steam condensing into water. So we'll go back to our table first. Okay, so this time it's vaporization, so it'll be 40.65 kilojoules per mole. Problem being, we don't have our moles. So we've got to do that whole little trick over there. So remember, moles is mass divided by molar mass. We have our mass is 63.07 grams. Divide the molar mass of water by now. I have it memorized. Doesn't matter. You might not. 18.02 grams per mole. That gives us a number of moles here. I'll just calculate this quickly. 63.07 divided by 18.02. Oh, that's actually a nice number. 3.5 moles. And now you just plug that into your formula. 3.5 moles. Q equals, so I'll go 3.5 times 40.65. That gives me 142.275. Remember, it's kilojoules. We're going to have to put that to 3 significant digits, so it'd be 142 kilojoules. Plain and simple, not too bad. The only difference there is you had to realize you had to take your grams and change that into moles. Okay, same thing here. I mean, just you're getting caught now with essentially unit changing, okay? So not really too much going on with that question. All right. This again is just essentially another rearrangement of the formula. So this time we're dealing with fusion because we're talking about ice. So Q equals NH fusion. What they're going to do is they're going to tell you you have 187 kilojoules. We have to figure out, okay, because two things. How many moles were in the ice? How many grams of ice? So there. Now, do we have an H fusion value for water? I think we do. I think it's a 6.01. Yep, 6.01. So that's going to be 6.01 kilojoules per mole. Now, I want my N by itself. So divide by 6.01 on both sides. N equals, I'll just do this quickly, 187 divided by 6.01 is 3.114 ... moles, okay? So if they want that in significant digits, again, I'll put this to 3. We'll go 31.1 moles, essentially. The second part of this question is they do want to know how many grams of ice you had. Well, mass equals moles times molar mass. Now, when I calculate this, the molar mass of water, as we all know by now, is 18.02 grams per mole. I just put that in there. No need to calculate that. One thing I will tell you here, this is our number of moles. One thing you're going to learn as you go through chemistry and physics, it's actually best to take through, you see this number here that was the long-winded, calculated, non-scientific notation form? That actually is the form that should go up into here. It gives you a more precise answer. So when I'm answering this question, I'm not going 31.1. I'm actually going 31.1148, on and on and on. I'm going to take that and I'm going to multiply it by 18.02. That gives me an answer of 560.688, so on and so forth, grams. We'll put it to 3 significant digits. That would be 561 grams. Anyway, everybody, I hope that you're starting to see the kind of how the algebra has crept back into play. So for vaporization and fusion, I think the biggest thing here is you need to figure out, are you dealing with fusion or vaporization? Once you have that, you can go back to this table and you can find the appropriate value that you have to use. Then what I would do is I'd go back to the formula and input some values and see what you need. See if you have to change any units. Nonetheless, I think you're finding with these chemistry calculations that they are somewhat repetitive. It's basically find the formula you need, input the values. Maybe you have to change units, maybe you don't, and then calculate the value. So algebra is a key point. Again, if you want to go over this lesson again, please re-watch it, go through sections. Now remember, you're going to have the answer, so try these problems. Keep trying them, get the answer. Check the answer key. Does it match? Does it not match? And then try to figure out why. Hopefully this has been helpful.